Today we'll be talking mostly about sampling and interpolation. So until now we already work with discrete signals, but we never really considered the case that okay, we're working with discrete. We just but today we'll see how you can we'll see some problems that will arise during sampling, both in 1D and 2D, and we'll specifically look at this thing called aliasing, which arises when you don't sample finely enough at the points, and we'll see what Nyquist rate is and Nyquist sampling rate is, and then we'll see um, what image resampling is, how do you upscale an image, how do you downscale an image, and how do you doing that avoiding aliasing. And then we'll see efficient ways to build this upscaling and downscaling operations. And then we'll see how camera works, basically how the image signal processing pipeline in a camera works. And we'll see the problem. I mean, how do you acquire color images, and the kind of artifacts that will arise there. And then we'll see about some other crazy samplings which arise in magnetic resonance imaging. Okay. So, okay. Yeah, so let's start with 1D sampling. So I'm choosing a signal which has two frequencies. One of the frequencies is F, and the other one is 1. So I'll just show you what my signal is. It's the blue line. It's just a second. So this is my signal. This ideally looks something. It's like a it's like a it's an oscillating wave which is carried by a very high frequency, which is F. And if you want to sample the signal without losing any information, we have to sample it at twice the what Nyquist sampling rate says is if you want to sample losslessly, then you have to sample at least twice as much as the frequency of the highest frequency in the signal that you're sampling. So we created this looks continuous, but ideally it's not. It's just sampled at a very high sampling rate of 800. So I'm just sampling time points between them, and sampling is just evaluating the continuous function at a particular point, like you're applying the delta function. So here first so if we take a very fine sampling grid, and if we sample all the at each point in the signal, then we end up with something like this. Okay, so now if we sample with a very good the sampling frequency here is 40. So yeah, I'm sampling at the rate of 80 now, which is I'm sampling each the points between second at the frequency of 80 points per second, right? So then you see that it samples perfectly at the corners, and you can imagine that the points in between, the lines joining between them are just straight lines, and you cover everything without losing anything, right? So let's say I sample at 35 hertz, and which is less than the Nyquist frequency. So yeah. Yes, it's yeah, you recover the perfect frequency, and it's yeah. So yeah, I was wrong there. I mean, it's not you assume it to be piecewise linear. Yes, you won't lose any frequency information. So here, if you assume that you're reconstructing with a frequency of less than the Nyquist rate, so you see that you obtain something like this. Your signal looks to you like something with something like a very low frequency signal. It's not the signal that you're actually measuring, right? So if you this kind of artifacts that arise due to insufficient sampling are called aliasing artifacts. So if you see, let's say I change my rate to 40. You see that this is not the signal that is actually underlying. So So it's important to consider that when you're sampling. So basically, I'll read it out. What it says is a band limited continuous signal can be sampled and perfectly reconstructed from its samples if it's sampled twice as fast as the highest frequency. So now we'll see how these kind of we'll see the exact replication of sampling that occurs in 2D. Okay, so I have another. So what I'm trying to do here is I'm trying to draw concurrent lines. No, not concurrent lines. They all intersect like spikes. I'll show you. So I'm trying to draw something like this, and so here it looks fine. You don't see many artifacts except the one in the center. So if you sample lines finely enough along the circle, then you see something like this. Okay, here it's still not evident, but then now if you want to subsample this grid into this grid, which means that you're sampling at a lower rate, then you will see. Let's say I'm scaling it by 2. Sorry. So you see this kind of artifacts. They're exactly what we encountered in the previous case. Here we're rescaling without applying any low pass filter. These kind of artifacts are called Moir artifacts, and they also, I mean, if you imagine, this is just a toy example, but if you can imagine, you have a texture in an image which is very fine. Then when you sample such areas, you get such artifacts, right? So and you get such artifacts when you sample them lesser than what the frequency they're occurring in the natural scene. Okay, so one way to avoid this is to apply some low pass filter before you do. Yeah. So I just took this image and I just sampled it by leaving one point in between. Let's say this image size is 512 by 512. I'm just choosing even points. Okay, and when you do that, you see something like this. It's exactly the same as what we saw in the 1D case. We are still evaluating the same function, but when we're not evaluating finely enough, you see these kind of weird things. So one basic remedy to do this is to cut the high frequencies before you downsample them, and just do the same. So that's what I'm doing. I just implemented some very basic a filter of which averages all the pixels that is nearby, and then it does the downsampling. Not yet. Yeah. I implemented it through convolution. It's on the spatial domain, so no Fourier transform yet. So when you do that, you get something like this. So here it's still evident, but it's less so than this one. You don't completely eliminate it, but you can get rid of some of them. Yeah. Yes. So how I implemented it is just I chose the center point, and then when I give it the number of lines I want to draw, it just samples what points I need to draw the lines until, and it just there's a MATLAB library called PIL, Python imaging library. So it just, when you give these both points, it just draws the lines for you on the grid. So you can look at it later. It's not interesting how I implemented it, but the concept is if you don't sample fine, when you're having high frequencies, you should sample finely enough. Otherwise, you'll end up with these artifacts, right? So yeah. So let's say now I want to I want to take a natural scene, and I want, so there are many ways of doing so. In the previous case, I just applied a very uniform filter, like a mean filter, just summing up all the neighboring pixels. like in a 3x3 grid. Now I want to do something. If you want to do something more sophisticated, like if you want to apply bicubic filter or Lankos interpolation, what Alex taught in the class, so you can just use these SciPy routines. You just there's a function in SciPy called SciPy.mis. I am resize. I think I need. There's also this function in other libraries, but so this function is going to expire soon. So I need to rechange the path. So basically, what I'm doing here is I'm trying to see different. I'm trying to compare different types of these low pass filters. Nearest is the case where you don't apply any low pass filter. You just choose the nearest point. I mean, let's say you're downsampling by 3 times, and you choose the downsampling grid, and then you choose whatever the point that is nearest in the high resolution picture, and then you just put it there. So there's no filter applied there. Bicubic is where it's a kind of filter where you assume some kind of you can have 2D bicubic kernels which are predefined. You can look it up. I don't remember them now, but they basically basically after before applying this downsampling, they just apply this bicubic kernel and then do the IM resize. Right, and the same thing with Lankos. You also have, I think, bilinear. Bilinear is where you'll see later bilinear. So yeah, so I'm just comparing all of them. So this is my original image. The grid and the lines inside this window, they look fine. When you downsample them with just nearest neighbor, you see that you're losing something here. And when you downsample them with bicubic, you see that you're kind of recovering them. While even though if you look at this line here, you're losing some resolution. It's not as good as the one here, but because you're obviously averaging the surrounding pixels, so you lose the actual content that is in there. But eventually you will you see that it is able to recover this high frequencies when you apply this downsampling prior to doing resize. Okay, the same case. I don't see much difference between these both, but I mean it's a choice. You can see some minute differences, but this is bicubic and this is Lankos. So now just the same thing. Now I am given an image in a smaller grid, and I want to put this image in a bigger grid. So what you can do is you can just place the points. Let's say you're upsampling by the size of 2. You can just place the points evenly, and you want to interpolate something in between, right? Then you can apply a low pass filter there just to fill these values. Or if you don't want to fill these values, you can just copy the value of the nearest pixel into this, which is also good enough. That's what again the same thing does. I honestly don't see any difference between these 3, but you can see that it's doing something because you're losing some information in the center wedge. So basically exactly the same thing. I'm initially choosing this picture, and I'm downsizing it, and I'm giving this as the input. I'm assuming this is my original image, which is sampled at a smaller grid, and now I want to upscale it. You can see the difference in the scale. It was originally 1400. I'm giving it as the input as 700, and then I want to rescale it back. This is using nearest neighbor, and nearest neighbor you search for the nearest one, and this is using other filters. Basically if they both of actually it depends on the scale of interpolation. If you're interpolating more than onto a more than this grid, then or probably you choose one of them, or I'm not sure which what exactly you put there, but it depends. Let's say you're sampling at four times more, then you can get some estimate of probably you average them. Otherwise, yeah, I think you average them. So yeah, let's recall how we were discussing about this sampling thing. So when you have a signal and you want to sample them, what we were doing was we are applying a low pass filter on the huge signal, and then we're picking all the if you're sampling at a rate of 2, then you're picking every even point in the signal as your low pass as your resample signal. So so doing this is inefficient, like we saw today in the class in the morning. So why is this inefficient? So basically you're applying this filter on a huge signal. Let's say you have a signal of 44 kilohertz. You have 44.1k points per second, which is the case of audio. And if you apply this filter on all the points, and then you're throwing them away, it's so wasteful, and that's and when you're implementing them actually on FPGAs and on real-time systems, this is a huge waste. So what you usually do is this thing called Polyphase. What Polyphase suggests is you have these noble identities, which we saw today in the class, which Alex proved, I think. So so you have what they say is decimating a signal and then applying a filter on the whole signal is equivalent to I mean, this is the one we're trivially doing without the use of Polyphase, and this is the modified one. So if you apply a filter and then you decimate, it is exactly equivalent to doing a low pass filter, doing decimating first and then choosing and then applying a filter on it. So so you see, initially, let's say we have this. This Z is just ignore the Z. It means just a shift. You're shifting your signal by one. So basically, if you ignore this, you can see that you're applying the signal here. I mean, you're applying the filter here, and then you're taking all the responses, and then you're throwing even one of them away. So instead of this, what you can do is you can decimate your signal, and then you apply a filter, and then add them all. I mean, you have to choose them appropriately, because you have to choose which ones to apply the filter on. Let's say so for the first one, you're choosing. Let's say you're decimating by 2. Then you have 2 such things. The rest of them are not there. Only you have 2 such lines. Let's say, and you. Basically, you choose every even one of them, and then apply the filter on that, and then you add them at the end. And for the odd ones, you apply it separately. So it's the same for while interpolating. When you're interpolating, when you're upscaling a signal, what we were doing was we're just imagining a grid. We're just putting even if you're upscaling by 2, you're just putting points in at every even place, and then we're applying a low pass filter on the big grid, which is also wasteful, because you can rather apply it on a smaller one and then apply it on the bigger one. So it's exactly the same. Even in this case, you just you upscale them, and then you apply you apply the filter on the smaller signal, and then upscale them, and then add them all together at the end. Okay. So now we'll see. Like there's a routine in SciPy which does this for you. You don't have to implement it yourself. Because it involves a lot of edge cases, and it's important to consider. So so let's say we have such a curve. Let's remove this. Let's say we have such a curve which is sampled from this equation. You're just evaluating it at 10 points between 0 to 10. Now you want to upscale this using your standard filters, which I mean using the resample thing that we talked about. Just you interpolate them on a grid and then fit a function to it. So let's say now your y looks like this, your original data, and then okay, the other way to do this resampling is to just choose this low pass filter in the frequency domain, and then just multiply by it, and then you rescale it. When you're rescaling it back, you can just take it to the higher sampling rate, which is done by this function. Ideally, the importance or the beauty of Polyphase is if you want to sample signals at irregular rates. Let's say you have a signal with sampling rate of 41 kilohertz per second, and if you want to convert it to let's say 42 kilohertz per second, how do you do it? Basically, you have to upsample by 42 times and then downsample by 41 times. And if you're doing it the standard way, like this, basically you're calculating the whole you're applying a filter on a huge 42k per second signal, and then you're applying the another down low pass filter on the huge 41k signal, which is wasteful. And this is particular polyphase can particularly perform better if you have such irregular sampling rates. So you can just use this resample poly function. What it takes as input is it's up, I think, and so okay, it works. Yeah. So what it does is you give it a signal, and then you sample, you tell it how many times you have to upscale it, and then how many times you have to downscale it. So if you want to increase it by 5 times, let's say you want to increase the sample rate by 1.6 times. You just say that you increase by upscale it by 5 times and downscale it by 3 times, or something like that. So here I'm doing 100, which is easy case. So I probably I50 implementation will still work well. But if you want to do it at a hardware level with irregular sampling rates, then we should implement this resampling using polyphase, right? So here I'm let's say, so now I want to no yeah, now I want to see how what it does. So what it essentially does is it just places these points at an evenly separated in a 100 array, and it just interpolates the ones in between using this also by the way, in this function, if you don't mention any low pass filter inside it, it just chooses some standard low pass filter, but you can actually give a filter that you want and pass it to it. I think you can give it in this in as an argument called window. So but we're not using it. I just took the standard one. So you can also pass the specific low pass filter that you want. So let's see what it does. So so this is the blue dots indicate the sampling. If you're basically sampling 100 points between 0 and 10. So this is kind of this is the one that F50 gives, and this is the one with poly gives. Basically they're the same with some edge cases because of the padding, but essentially they're the same. Yeah. So what is important to notice is here, if you're sampling with irregular sampling rates, then it's really useful. With irregular, sorry. Yeah, sure. Yeah. Yeah, sorry. This is the original signal. This is the original signal. You can just sample it very heavily and see if it's overfitting or not. Just a second. So this is the original signal. Kind of, yeah. But it depends on what kind of interpolation you're choosing inside. Depends on the low pass. You choose some interpolation as a low frequency, right? So it depends on that. So this was the original signal. So yeah. So now we'll see. So now we'll talk about how actually the cameras work, and there are two different terms, sampling and quantization. So we'll see what it means in the setting of image processing. So how a camera works is you basically have a lens, and then followed by it you have this thing called color filter array, and then you have a pixel array where your pixels are formed, and then you can there are two different types of sensors. One of it is called CCD, or charged coupled device, and the other one is CMOS. So essentially what happens is when the light comes, it just you have a lens which focuses onto this particular grid where we're doing the sampling. So this is the pixel array, and over this grid we have something like this. This is called as a color filter array, which is essentially like an optical element. What it does is it just filters out the light which is not in this frequency, that to not pass through this filter. And we have them arranged in this particular pattern. You see that it's green, red, and so on, and you have more greens than red and blue, which is because we are more sensitive to green perceptually, or you can just implement anything otherwise. So basically the light comes, it focuses onto this grid, and in this grid, in CCD, what happens is it's these photons are converted into charge, and they're stored in a capacitor in CCD, and in CMOS they're immediately sampled, and you collect them using a digital circuit. This is kind of similar to what happens. CMOS is kind of similar to what happens in the memories at a hardware level. So it's exactly the same as this. And so what quantization means in this setting is how sensitive your filter is. So let's say you're sampling using, let's say you're imaging using a CCD camera, which are not much in use now. CMOS is everywhere. But in the CCD camera, I'll not mess it up. So first, what quantization means is it's basically how sensitive is your sensor, which means let's say your light is incident for 0.1 seconds, and you will get a range of number of charge that is accumulated, and if you can sample finely enough, then if you can collect it properly enough, then you can basically then you convert it something into between 0 and 255 according to what charge you are accumulated there. And this 0 to 255 is basically you have 8-bit encoding in this for each pixel. It's 8-bit quantization for each pixel. And if you have a better sensor, it can also give you 16-bit or even more precise value of the color that is induced there. Okay. I have no idea, but yeah, it's something like that. I mean, it's basically you have very good, very fine precision of the number of of the pixel values there. So yeah. So if you take it to an extreme, so this CMOS is proposed by this guy called Eric Fossum. So after when CMOS was initially proposed, it had bad quality and it didn't have a global shutter. Like you can't control each pixel at a time, which you can do in CCD, and it had really bad quality. But soon CMOS sensors caught up, and they're manufactured even in our camera. There are some DSLRs which still have CCD, but most of them have CMOS. Yeah. So and all of these cameras have this color filter array, which we'll use in a bit. So what Eric Fossum also recently proposed is such a camera where you have infinite sampling. Basically, you are sampling 10^9 dots. This image is just the eye of Lina, and the whole sensor they have is like a 1 giga dots, but at each pixel it's just 0 or 1. The quantization is just 0 or 1. So basically you can get the whole image as a binary, but it doesn't when you look far away, it doesn't seem like binary anymore. So you can basically reconstruct a good quality picture from this one, so which is also one of the running projects in the lab. So yeah, here I just wanted to mention this to differentiate between sampling and quantization. Here we have infinite sampling, close to infinite, 10^9, but you don't have the quantization. And in this case, you have limited number of this pixel arrays, but quantization is good. So that's why you get clean images like this. So now let's simulate what happens inside this ISP. What ISP means is when you get such a data from that is passed through this through this color filter array, you want to use that data and you want to form the actual color image if you observe here, you can see that it's when we obtain the image, it's not really colored, it's just a color afterwards. So we'll see how it works. So let's see. So I'm first creating a CFA channel, which is exactly, oh, yeah. So what happens is, basically I had raw data which I got from a camera, and this is the raw data. And so what it has is it also has some information about what kind of grid it was sampled from. So it knows if it was using such a color grid. So you just what you have to do is, you just assume that at every pixel you go and you say that, yeah, okay, are you green or not, to every pixel, and then you say the same thing for blue and red. So you get a grid of green pixels, blue pixels, and supposedly green, red, blue, green, and red. So what you do next is, now basically you have pixels at on a grid which is not sampled finely enough. Then it's basically you have pixels on a different grid, and now you want to sample it back to the grid of the original image. So what you do is you just apply a bilinear filter. First, what I want to show is, I just wanted to reconstruct images from this undersampled grids and show you how it looks like. Then you get some artifacts which look very similar to this Moir artifacts that we saw. And then what happens is I apply a bilinear filter on it. So what happens is you get the blue and green values to every pixel on the three red, blue, and green on the three arrays, and then you just reconstruct the whole image, and then you stack them up, which is basically your RGB image. So each pixel has 8 bits of 3 of them, so you have 24 bit values for each pixel. And after that, what I wanted to show was the rest of the operations. Like, so what happens ideally in what I might have is, okay, I have some buffer which is saved from the previous time I ran it. So these are the, so let's look at this. So let's remove this. This is not important. So this is what is acquired when you apply this red mask. When you apply this red mask onto my original image, which is the raw data, you acquire something like this. So see, these are the pixels sampled by the red color filter array, and you get the same thing for green, which is supposedly more, and also blue. So then what I wanted to show was, so what happens here is, now I'm applying low pass. So now I want to fill all these values on the grid, right? So each pixel should have both red, blue, and green values. So now I'm just applying this low pass filter on this convolved image, and I'm convolving with the low pass filter on this red image, green image, and blue image, and then I'm stacking the channel. So eventually I'm getting colors here. So it was originally, you didn't know what color it was. We'll see more in the next run. So eventually I'm getting colors here, but I don't know what is the ideal sampling. So what I can get from a camera is how what is the RGB for a certain, we imagine a gray world, and you find what is the RGB for a specific color, which is usually white for calibrating. So then what you can do is, then you can just do this thing called white balancing. I just chose some arbitrary value for this, but if you get raw images from any camera, you also get this information of how much balancing you need to do, and then you just apply this. So if you think of an ISP, when you click a picture with your mobile phone, it just acquires this raw data. Rest all is done in software. So what happens is, first you do this demosaicing, this thing which what I did with interpolating the red, blue, and green values to all the pixels. It's called demosaicing, and then you do some denoising, which I'm not doing here, but ideally if you have some noise in the sampling, then you can just do some denoising there, and then you also have to do some color correction and gamma correction and all that. So those are high level operations that happen in an ISP. So basically all the I mean, for example, if you think why Apple, if you think of Apple phones and why they have why they click good images, it's basically they have good sensors for sure, but their ISP is so good that it optimizes for the best viewing on an iPhone. Let's say you see a iPhone image on a different screen, it doesn't look as good as how it does on the phone. On the iPhone or any Apple products. So the key thing is that this whole ISP is really important, and it does both low level operations such as demosaicing and high level operations such as gamma correction and all that. So eventually you end up with a color image which you didn't have earlier. Uh, so now there are some recent works, like in the past 6-7 months. What they do is they just take this raw image from some camera, and then they train a neural network which basically outputs the color image, which is beautified, applied both high level and low level corrections. And actually one of the works was done by one of my friends in the lab. So what they showed is if you take a Samsung S7 camera, and if you sample it and if you get the raw data from it, just these raw files, and if you apply his network, his method, then the whole thing happens inside a network, and you can get better looking images than what actual Samsung ISP provides. So it's originally it was done using this bilinear interpolation and all these traditional methods. Now people are more moving towards data-driven methods. So after this, so this is your sampling here you're still sampling on a 2D grid, which is you're spatially sampling them. Now let's look at somewhat where you sample in not a spatial grid, but you're sampling in some other domain, and what kind of artifacts you can face there. So if you consider magnetic resonance imaging, I'm not going into the physics of it much, but what happens is in magnetic resonance you basically acquire the k space or the frequency space of the image. So you go to every pixel, you acquire this frequency domain image, and after you acquire the whole thing, you do an inverse Fourier transform, and then you get this image, and you don't have it from the beginning. So I'm not going into the physics of it, I'm sorry. But basically you acquire the whole each pixel in the frequency domain. So the one bad thing about this is if you're acquiring data in frequency domain, you can't stop it once you acquire half of it, because you get garbage. So that's why MRI takes like forever, like 20 minutes for acquiring a single 3D volume. So if you want to undersample, let's say you want to reduce the time it takes, and if you want to undersample the K space, so let's see how it looks. So I'm just importing some image, some slice on the brain which has cancer here. So I'm just looking at the K space. This is what you're acquiring with a real MRI machine. And then I'm doing some sampling here. So I just want so one other constraint that you have when you're doing MRI is when you're acquiring, let's say you acquire the first pixel, right, 0 0. You can't randomly acquire 0 3. You have to be continuous because otherwise you'll burn the magnet basically with which you're acquiring. So there's a constraint that you shouldn't have strange shifts. So you have to keep acquiring in continuous trajectories on this 2D sampling grid in frequency domain. And then what you can do is you can skip a few lines in between, which is also people complain about it, but still it's better than sampling at random places. So let's say you acquire with this sampling grid. Basically, you're removing values in vertical columns, and you're half of the values and half of them you're keeping them. Okay. So now I apply this mask onto my K space, and I reconstruct my original image from it.